slide from actually the last lecture of the class, the last time I taught this, so it gives you an idea of the kind of things we're going to do. I'm going to take 5 minutes to read this, and then I'm going to ask you to get in your groups of 3 or 4 people again, and then talk about what is the question asking, where might you start, what kind of things would you need to know to solve a problem like this. This is to give you an idea of the types of things you'll be able to do when we're through this class. So take a minute to read. What do we need to find? Everybody. Fractional conversion. Okay, so what's fractional conversion? What's it sound like? How much became the product? Yeah, it has something to do with how much got reacted and became the product. That's what we often care about as a chemical engineer. So how much is converted into product? What fraction is converted? What's going on? Let me call it something. Danny, what's going on in this problem?
So you are trying to keep the temperature from dropping, probably to keep a higher rate, depending on the rate constant of it. And
you want to control the temperature or reaction? Good. What else?
Well, you know that the temperature is dropping, so you have to achieve and calculate how much you're losing or the actual rate of the temperature.
Okay, so we have to know something about the temperature, how fast the temperature is dropping. Yeah. Nikhil, you got more to add? What else is going on here?
The time of how much product is coming in, or the flow rate, which I'm assuming is how much we're adding reactants to. And then we're being told, the temperature, which I'm assuming is the temperature of the products.
Yeah, okay. So one of the first things we'll always do as a chemical engineers, we'll draw pictures. So what's the system we're talking about? What is the chemical engineering unit? And Waisha, do you have any clue where's the reaction going on?
Some sort of reactor.
Some sort of reactor. So as a chemical engineers, we'll often start by just making a picture of the unit operations that we're doing. So in this case, a reactor. So Nikhil said we got to worry about some kind of flows of stuff going in. We got to worry about some kind of temperature in the reactor. And we're worried about what's coming out and what fraction it converts to. So we want to know the fraction of conversion. What else is going on? There's a group I haven't called on yet. Anybody else want to volunteer to talk about what's going on in the system? Yeah, Brendan.
We have, is the V for vapor?
The V is for vapor phase, yes.
So we have a vapor going to a vapor and a gas.
Yeah.
So we have to make sure that there's some sort of molar equilibrium going on here.
Equilibrium, yeah. Equilibrium is an interesting concept. Are we in equilibrium? Why not? There's no backwards arrow. That's true. That's a really good clue. There was another hand up? Yeah, Jack.
So there's a flow rate, so there's constantly being reactants pumped into the reactor.
Constantly stuff going in. Yeah, I think you're all dancing. What happens at equilibrium? Forward rate, backward rate are the same. Free energies are at a minimum. We're changing stuff here. We're changing matter here. So we're out of equilibrium and things are going toward equilibrium. That's why stuff is spontaneous and happening. But we're not in equilibrium. So usually we're out of equilibrium and we're pushing things. Yeah, just putting stuff in that's different than the system. We're disturbing the system that would keep it out of equilibrium. Yeah, so we're not in equilibrium, but equilibrium is a really good idea to keep in mind because that gives us a base state to think about. All right. Yeah, so what might we need to know to answer this problem? Oh wait, there's more going on here. Tell me about heat. So maybe there's a heater here or some kind of fire. And I've got some kind of heat transfer in the reaction. So I've got stuff going in, I've got heat going in, I've got stuff coming out, I've got a reaction. What might I need to know? What else? So what are we going to need to find out? We're going to need to know something about how much energy the reaction gives off. You have some in the back? The heat of reaction would be important. Maybe something about the thermodynamics, maybe something about the kinetics of the reaction. How fast does it happen? What else might we need to know? Yeah, Daniel.
If there's any runaway reactions at like lower temperatures or higher temperatures?
How does the reaction respond to temperature? Is there any runaway reactions? I would hope the answer is no. But certainly in the design scheme, we think about where are the safety concerns, where are the boundaries of stability, and we keep that in. So stability, and we actually won't get to till your senior year in process control, and then you'll ask that question, but we'll do the steady state solution here where we assume it's under control and we get the conditions to it that it actually works out. Yeah. What else? People mentioned some things about change. One thing how does the system change in time? What's the role of time with this situation? Can you tell me? Sebastian.
Ethanol is absorbing the heat, so you have to keep pumping in heat.
Keep pumping it in because it's absorbing the heat. Brendan?
Over time, our reactor wouldn't change much at all, because whatever comes in is coming out.
Is the reaction going to change at all over time? Is the reactor going to change at all over time? Adding stuff in, reaction's going on, that's taking in heat. I'm putting heat in, I'm taking stuff out. Okay, when you first start doing this, if your intuition tells you things are going to change because you put things in and you watch it change. You usually do things in chemistry labs, a batch experiment. You add stuff and you watch it change over time. This is probably happening in a chemical plant that's been running all day. It's been running for weeks, maybe all year. You're trying to keep it steady production. When you get this steady, it's not changing in time. At any given instant, there's stuff coming in, there's stuff reacting, heat balancing off, and stuff going on. This is all at what we call steady state. That means nothing changes with time, so dx dt equals 0 for anything that can change in time. So it's not getting cooler, it's not running away. We're looking at everything is steady running. Okay. So I don't know what would be a good example. Turn on your bathtub. Turn off the faucet to your bathtub. Leave the drain open. Yeah. And don't turn it on too high, it's going to overflow, but at some point, stuff coming in will equal what's going out. Things are flowing through, but there's a steady amount of bathtub and nothing's going on. Okay, so, all right. So there's a few concepts. By the time you're done with this class, you're going to be able to calculate the material going in and out, the reactions going on, the energies going in and out. I think you should have a little bit of, it sounds like you all have a lot of thoughts about what's going on because you've got the background from chemistry, you know some things about heats of reaction, specific heats, balancing chemical reactions, kinetics, but we're going to put all the mathematical formalism that you can see this and just write down a few equations and chop all this out. Plus all the jargon like fractional conversion or feed or any of that. So where do we start? Let's talk about chemical reactions. Because you know this, and this is kind of the heart of the process. We want to take stuff and turn it into other things that we want. And I think you already know how to do this. So let's just start there with an example. Let's say everybody wants better iPhones and tablets. Let's make some silicon. So we have some microchips. Let's take silicon chloride and hydrogen, and I want to make pure silicon. That's going to give off hydrochloric acid, so we want to do this to make pure silicon to make microchips in a solid form. Is the equation balanced? No. Can you balance the equation? Take 30 seconds, balance the equation. 2H2, 4HCl. How many people agree? Okay, good. So how do we do that? What's the principle, Lily?
You just like see what the elements you have on each side and then balance that.
Elements on each side, we got the same number of atoms on the left as we do on the right. Okay, so that's easy enough. I want to put a little more formalism to it, just so we have some math to as we go forward and get more complex. So I want to start with stoichiometric coefficients. I'm going to call these nu sub I for each compound I. This is the Greek letter nu, N-U. And nu I, we're going to use a convention. Nu I is negative for reactants, and nu I is positive for products. So in this particular case, we're going to have nu of H2 is going to be -2 because it's a reactant. There's 2 of them. I'm also going to have nu for SiCl4, silicon tetrachloride, and what's that one going to be? That's a -1. Let's see, nu for silicon is going to be, everybody, nu for HCl, everyone, it's 4. Great. So then we're also going to let epsilon sub Hi equal the number of atoms of type H in compound I. So epsilon for silicon in silicon tetrachloride is how many atoms of silicon and silicon tetrachloride is 1. Epsilon of chlorine in silicon tetrachloride. How many atoms of chlorine in silicon tetrachloride? 4. Okay, so this is really stupid, right? Epsilon of hydrogen in H2 is 2. Epsilon of silicon in silicon is 1. Epsilon hydrogen and HCl is 1, and epsilon of chlorine and HCl is also 1. So that equation is balanced when the number of atoms are the same on both sides. So I want to write an equation that means that, and I'm going to use these here. So what I want to say is the silica's here, and they're the same as over here. So a balanced equation means that the sum of epsilon Hi times nu sub I summed over all compounds I. So we go through each compound, take the stoichiometric coefficient of the compound, that's the number of atoms of that kind of atom in the compound. We add them all up, and that equals 0. For silicon, I'd say, I go through each of the 4 compounds. So we have epsilon for silica in silicon chloride times nu of silicon chloride for I equals 1 for the first compound, for I equals silicon chloride, plus epsilon for silica in H2. How much silica is in H2? Times nu of H2. We didn't define that one over there. How much silicon is in H2? 0, so that's okay. Plus epsilon of silicon in silicon, nu of silicon, plus epsilon of silicon in HCl times nu of HCl. then you plug in numbers. Silicon and silicon chloride, 1 times mu SiCl plus, this one is 0, plus 1 times mu silicon plus silicon and HCl, that one's also 0, equals 0. So the equation I get out of this is mu SiCl plus mu Si equals 0. And does that match the solution we came up with earlier that you guys just told me? So the stoichiometric coefficient for silicon, chloride, and silicon, one is -1, one is 1. That's consistent with that equation, right? Okay. It's actually not unique. I could have, for that equation, I could have gone with 2 and 2 or half and half. So, you know, for these, you always have to choose a basis. We have to set one of them to 1 or something else convenient. So nitric acid is used in industry all the time, in particular to make nylon and other polymers. Let's say NH3 plus O2 goes to NO plus H2O. And let's write an equation. Let's see, if we want to balance the nitrogen atoms, so I would put there's a nu here for NH3, a nu here for O2, and a nu here for NO, and a nu for H2O. All the reactants should be negative, right? Because these are negative numbers. When we write the equation, it's, sorry, this one. Those are negatives. Okay, so if I'm going to balance nitrogens, I'm going to have mu NH3 times the epsilon of N in NH3 is 1 plus 0 equals mu NO times 1 plus 0. So I get mu NH3 equals mu NO. I balance the oxygens. What equation do I get? Mu O2 plus mu NO plus mu H2O equals 0. With me still, how about H? Joanna, you?
Is it 3 mu? Is it mu?
Mu?
Mu NH3 plus 2 mu H2O equals 0.
It's 2 M8 mu H2O equals 0. Okay, great. I presume you guys have questions?
Should it be 2 mu O2 for the O equation?
Yep. Thank you. I'll make mistakes at the board all the time, so please just point them out, especially for the videos. It's not there for everyone to. Yeah, but more importantly for your notes, so you know. Great. So we just made a system of 3 equations. And how many unknowns do we have? We've got 4 unknowns. How do we solve that? 3 equations, 4 unknowns. Yeah, that's right. So what do we need?
Gaussian elimination.
Well, Gaussian elimination, dude, with three equations, 4 unknowns. Gaussian elimination help us?
That can work.
Yeah. Page.
We need to fix a value.
We need to fix a value. So we need to pick a basis. Pick the ChemBE word, a basis. So we'll probably say something like, we just set one. Mu NH3 equals 1. We just pick one of them. Now we've got 3 unknowns, 3 equations. Now you can do that, right? Okay. Okay,
Are you
Jen.
guys have a negative sign on the first equation?
Maybe. This one or this one?
One's a product, one's a reactant.
Okay, so, and yeah, good. so let's see, nu times epsilon plus nu times epsilon plus nu times epsilon plus nu times epsilon. So yeah, these should all be added together. Nu NH3 plus nu NO equals 0. Then if I flip one to the other side, nu NH3 equals nu NO. That's, you're right, that'd be a negative. Thanks. Solving matrix equations. This is appendix A1 in Murphy's textbook, so you might be able to breeze through there. It's got more than we need to know. Okay, so 3 equations and 3 unknowns we can write as a system of equations. So consider, I'm going to drop the news for a little bit. So let's just go with u plus v plus w equals 6, u plus 2v plus 2w equals 11, 2u plus 3v minus 4w equals 3. So here's a system of 3 equations and 3 unknowns, u, v, and w. So this is, when we do this from balancing equation, that matrix comes out pretty sparse. There's a lot of zeros. A sparse matrix has a lot of zeros. This one's full. I've got numbers for all of these. But in general, I've got 3 equations, 3 unknowns. Everybody knows, everybody solved things like this before, I presume. But I just want to review briefly how we can go about these. So if we take 3 equations and 3 unknowns, and if they are linear, then we can make a matrix equation. Everybody knows what I mean by linear. So linear means I've got terms like 2w, but not 2w squared, or not 2w times v. And no products. Everything's got to be first order, a variable to the first power. Okay, if I do that, then I can write a matrix equation. I can copy these numbers, coefficients 1, 1, 2, 1, 2, 3, 1, 2, minus 4. I can multiply or dot product that against the vector variables, u, v, w, and that will equal a column vector 6, 11, 3. So it's the same system of 3 equations and 3 unknowns. So when we read this, the dot product would go across a row, and you multiply down the next column. So we have 1u plus 1v plus 1w, u plus v plus w equals 6 over here. So we can translate the 3 equations for those 3 rows. Yes, any questions on this? Are we reading? Okay. I can take that matrix, I can call it A. I can take that column vector, and I can call that X. I can dot them together, and that can equal the vector on the right-hand side, which I could call B. AX equals B is the standard linear algebra form, matrix form for a system of equations. I could also write this, so here the double underline is a matrix. It's a one that has a 2 by 2 dimension. The single underline is a vector. I can also write this as Aij times x of j summed over each j equals b of I. So if I label these rows j, or these columns j, j1, 2, 3, I can take a11 multiplied by x1, a12 is 1, multiply that by x2 is v, a13 is here, multiply that by x3 is w, then I get b1 is 6. Okay, questions here. So now this is starting to look like our new's and epsilons, right? Okay, so this is an equation, and this is actually 3 equations. So we say for all I, so I equals 1, I equals 2, I equals 3 are those 3 equations. So there's a whole bunch of linear algebra behind this. If you take a linear algebra class or your DFQ class, you'll see some things. There's conditions to when this works. Everything has to be linear, first of all. If b is 0, that's not going to work. Just like in algebra, if I had 2 times x equals 0, you can't tell me x, because the equation is singular. Anything times, no, if I said you, let me think, 2 times x equals 0. Well, it's kind of like a similar equation. If b is 0, you might not be able to answer it because you might not have a full system of equations. What else? You need to have a square matrix, which is the same as saying we've got the same number of variables and it's the same number of unknowns, because the number of unknowns is the rows, and the number of number of unknowns is the columns, and the number of equations is the rows. So those have to be equal. We have to have a square matrix. And then there's also some tricky things like the reduced row echelon form has to have no zeros on the diagonal. So if you rearrange this in a certain way, there are other ways this can come out to actually where this is a matrix form that's kind of like 0. You have 0 times x equals 5, and you don't know what x is. Okay, so sometimes it's not solvable, but in general, that's it. So how can I solve these systems? You should have a few different ways of solving these systems by now that you picked up. So one is, I think, what you just did in your head, balancing these equations, which I don't know what you did in your head. So we can do Gaussian elimination. That's the second time we've heard that here. How many people know Gaussian elimination? Okay, cool. I'm not going to teach Gaussian elimination. If you do it, that's awesome. If you've got any computer, it's a nice computer sciencey way, a bunch of rules to go through things. It's also in the appendix, so you can go through that. But yeah, one way is you could do Gaussian elimination. If you've never heard of it, I recommend looking at the appendix. It's kind of burdensome, right? It's very tedious. You go through each little tiny step. It's kind of like doing all this just to balance an equation when you do it really easy. So, and nobody actually does Gaussian elimination. You might use it as a basis to write a computer routine. That computer routine's been written. So, what else? Page.
Take the inverse of it so you can solve for it.
Yeah. Okay. So a dot x equals b. She said take the inverse. So if we took the inverse of a minus 1, and we dot it with a, and do that to the other side too. Inverse of a times a gives you the identity matrix, times x, which is the same as x, is the inverse of a dotted with b. So you can take a matrix and you can flip it around and get an inverse. There's a procedure to do that. I'm not going to go through the mechanics. How do you get the inverse of a matrix besides going through mechanics? What's the easy way, engineers? Say we give you a 10 by 10 matrix. What would you ask for the inverse of that matrix? Calculator. Who else could you ask?
MATLAB.
Huh?
MATLAB.
MATLAB. We'll talk about this afternoon and tomorrow. So in MATLAB, you say INV-A. You get the inverse of A. It's that easy. So we'll do that. And anything else? Who answers all your questions today? You can probably put this in Google. Actually, I haven't tried, but I bet if you put it in Google in MATLAB form with commas, 1 comma 1 comma 1 semicolon 2. If you had a way of entering this, I'm sure Google would do it for you. So maybe somebody can try this. Google, certainly Wolfram Alpha, which is probably what Google's going to use. Wolfram is the company that makes, not MATLAB, Mathematica, which people don't use anymore, but they're now on the web and you can ask them lots of questions, and then Google's got it plugged in. So I'm sure if you put the matrix in there, it would flip it over for you. All right, so I didn't quite synthesize this together. You can take these nu and epsilon equations. You need to pick a basis, otherwise you don't have a square matrix. Pick a basis, and then you can turn it into a matrix. You can turn it into a matrix form without choosing a basis, but then you have 3 rows or 4 columns, and then you can do some linear algebra checks to move a column over. That's also discussed in the appendix. You can also just plug in a number for one and then rearrange it and make your matrix, and then you have this solved. Okay.